So, what do we do? Let's get back to the plenty of room at the bottom idea. When Richard Feynman talked about going down into the atom to find room for information, he only went as far as the electron shells were concerned, because there's a little bit of energy in those electron shells, and there's enough energy there that you can manipulate so you can store information. But if we go just a little further into the atom, which is the nucleus of the atom, we suddenly find we are confronting the greatest storehouse of energy in the universe. 98% of the energy stored in matter is stored in the nucleus of the atom. Now, the best way to approach this subject is to think of the famous equation postulated by Albert Einstein in 1905, which is E equals mc squared. Now, I know you have heard of it. I know most people in the world have heard of it right now. Mariah Carey just put out an album. Her latest album is titled E equals mc squared. So it's pretty much in the public domain by this time. But how many people understand what that equation means? E equals mc squared. What it says is energy and matter are equivalents. They are interchangeable. That energy can be transformed into matter. Matter transforms into energy. Energy and matter are essentially two different aspects of the same thing, the energy-matter continuum of the universe. There are two things in the universe, energy and matter. They can transform into each other. Before Einstein, people had recognized that there was a law of conservation of energy. This was, the conservation of matter was actually first discovered previously in the end of the 18th century. At the time of the French Revolution, there was a French chemist, Lavoisier, who had worked out these very close calculations. He would burn a piece of wood, he would weigh the wood, then he would weigh all the gases. You know, the gases would disappear, people didn't think about them. But he collected the gases, he weighed them, he weighed the ash, and he found that they always weighed exactly the same. That matter could change form, it could change from a solid to a liquid to a gas, but the amount of matter was consistent, was always the same. Matter could neither be created nor destroyed. The conservation of matter. This was well known by the time of Thomas Jefferson. Then in the 19th century, a series of very brilliant scientists worked out a similar principle for energy. That energy, what changed forms, it became heat, it became motion, it became light. There was a very potential energy, there was various forms, but the amount of energy always remained the same. Once again, energy could neither be created nor destroyed. The big point to get over there was heat. Everybody thought of heat as a fluid and that you could create unlimited amounts of it, but they Rumford finally realized that heat was a form of energy, and it could only be created by expending other forms of energy. So this is what we do when we create electricity. We change coal into heat, which becomes steam, which becomes electricity. Now, what Einstein postulated that no one had ever really dreamed of before was that there was also a continuum between matter and energy. That matter actually disappeared completely and became energy, into the form of energy, and vice versa. Energy could be transformed back into matter. But the important thing there is the coefficient, c squared. C squared is the speed of light squared. The speed of light is a very, very, very big number, 186,000 miles per second. When you square it, you get a number of the order of magnitude of about a quadrillion. 1 followed by 5 triple sets of zeros. Big, big, big number. The point is this. The coefficient sits next to the m, the mass. When you transform matter into energy, it has to be multiplied by a very, very, very big number. In other words, a very, very, very small amount of matter transforms into a very, very, very large amount of energy. Now, what we didn't realize, what we never realized when we go looking for matter, the place to look for matter is in the nucleus of the atom. And this was not at all recognized in 1900. It wasn't when Einstein formulated this equation. He didn't even really know it applied at all to the energy transformations we were going to be exploring. But what happened over the course of the first half of the 19th century is that little by little people began to recognize the structure of the atom, what it looked like, that it had a nucleus, that the nucleus was by far the most dense concentration of matter. And just to get an idea, if an atom were the size of a large auditorium, the nucleus, in terms of sheer dimension, the nucleus would be about the size of a speck of dust. And yet, 99.9% of the matter in that atom is concentrated in that little speck of dust. So it's a very unequal distribution, but that's the way the universe is. So, up until the 20th century, the early 20th century, we spent most of our time rearranging electrons and changing the energy stages and deriving energy from those transformations. What scientists began to realize in the 1920s and 1930s was that the real repository of energy in the universe was in the nucleus of that atom. Now the question became, can we ever access that energy? Can we ever get access to that energy? A lot of people thought we couldn't. Ernest Rutherford, who discovered the nucleus, said, no, you'll never be able to access that. Albert Einstein said, wasn't completely skeptical, but said it's going to be very, 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 very difficult, almost impossible. But there were some other scientists, just step by step, nobody had any real idea where they were going, but just step by step they began to explore, and they found, Marie Curie actually realized this before anybody, they realized that there was a phenomenon known as radioactivity. There was energy coming out of matter that nobody quite understood. And it was finally recognized that where that energy came from was that the nucleus itself was changing, was splitting into smaller pieces. And that with that shift, with that splitting and that change, there was a release of energy. And actually, as they calculated it, they realized the release of energy from changes in the nucleus was going to be vast, vast amounts beyond anybody's previous dreams. So, fortunately or unfortunately, what happened is World War II came along, just about the time people were realizing this. And of course, the realization on both sides was, my God, what if somebody makes a bomb out of this stuff? And that story is pretty well known to everybody, that a lot of American scientists thought the Germans were going to be able to do it. The Germans were working on it, in fact, but never had too much success. Hitler actually had the post office working on it at one point. But we did succeed, and we invented a way of accelerating that breakdown of the nucleus to an unbelievable degree. I mean, everybody thinks if you get your hands on a little uranium, you're halfway to making a bomb. People don't realize the incredible technical sophistication that is involved